So I'd like to talk about our service. It's a real-time search service, and it runs on MySQL. And let me explain my background. My name is Kazuho Oku, and I used to be a web browser developer. But now I work for a groupware company called Cybozu, which is one of the largest groupware vendors in Japan. And this presentation will be uploaded to my weblog, so if you're interested, please download that. Okay? Let me explain about the web service that I created and I had to optimize. And it's a web ranking service started in the summer of 2007, and it's one of the Japan's largest web access stat service. And currently, it accepts access information from about 10,000 users every day, and the number of access information collected is about 1 million per day. And it's like Alexa, but it's semi-real time, and it collects per URL information. So in other words, it's something like a automated social news service that lets people to find out what's being hot or what's upcoming. So, and it's like something like between Google News and Gig. And it calculates what information is important is by using the access numbers instead of using page rank or the number of digs. And we can search the collected access information by, for example, category or keywords or by URL. Those things are possible. And so this is our top web page. And there are many rankings. And this is, for example, full text search using keyword Oracle in Japanese on 21st of April. And all the news are about the acquisition of some microsystems. So it's a time-based search engine, actually. So currently our data set is about this size, with about 150 million URLs and 400 million number of accesses being stored. And for us, sharding is not a good option, since we need to join the tables and aggregate them to create rankings. For example, we have to search the URL by prefix or search by keyword, and then join the result set of URLs against our access data to create the result. And so we have to, so the best way was to store the core tables on RAM. So yes, we decided to keep URLs and access stuff on RAM by compressing them. And by compressing them, we can gain both size and speed. Also, we created a new message field, or we use techniques to limit the load of pre-computation. And we also have our own cache system, and we run our full text search database on SSD. And our servers are like this. So our main server running MySQL and Apache is a 4-core Percona system with 64 gigabytes of memory. And we have a full text search server, well, which is pretty old, and we have some helper servers. That's all. And by the way, this is a graph collected by Percona, and you can see that. It's a graph of the long tail of the internet, and as the access count decreases, the number of pages increase. So when we compress the data, we have to take care of the long tail. We have to compress those pages which are rarely being hit. So first I would like to explain the techniques we use to compress the URLs. The challenges were that URLs are too short to use common compression techniques such as gzip. And the other thing is that we want to do a prefix search while the URLs are being compressed. And the answer was to use a compression method called static PPM. Well, it's actually a prediction model, and a compressor called range coder. So static PPM is a prediction model called prediction by partial matching. And if you consider a URL, what's the next character that comes after .co? And you know it's M in most cases. So that's the way of how to predict the next character by partial matching. And PPM is also used by compressors such as 7zip or those. So it's quite a good way of creating a compressor. And static PPM is a variant of PPM with static probabilistic model. And within the URL, there are many common patterns being shared. For example, as I said before, what comes after .co is M in most cases. Or what comes after .ht is in most cases M. So many URLs share the common pattern, so we can use a single prediction model to reach a good compression ratio. And next, about the range coder. Range coder is a fast variant of arithmetic compression. It's similar to half-line encoding, but it's better. And for example, in the case of letter M after .co, if M was expected to come in 75% of probability, then it will be encoded into 0.42 bits. So it's pretty very good compression. And the other aspect of range coder is that compressed strings have the same sort order as they do in uncompressed form. So we created the compression functions by building a prediction table from our stored URLs. And we optimized an open source implementation of a range coder using SSE instructions, and then link those two to create MySQL UDFs for compression and decompression. And we rewrote the server table, like changing the schema from using varchar with unique index to a binary storing compressed form with unique index. And since the sort order is being preserved in compressed form, the prefix search using like operator could be changed to a range query, like saying URL compress from this range to this range. And the upper bound, the last character of upper bound is 0 because slash is character 0x2f and 0 is 0x3o. So if within the range, it are the URLs below example.com. So we can do prefix search in this form. So the compression ratio we achieved is 37%. So the size became nearly 1/3 of the uncompressed form when we use a prediction table of 4 megabytes. And the speed of compression and decompression is fast enough for us, since we can compress 570,000 URLs and decompress nearly 300,000 URLs. And actually, prefix search became faster faster in compressed form, since shorter indexes lead to faster operation, because we only have to compare the bytes until they become different, and the number of bytes we have to compare becomes smaller. And talking about compression, I'd like to talk about InnoDB compression. And these kind of compression techniques can coexist. So this is the benchmark I did, and from a non-compressed table, by compressing URL using our algorithm, we gain the table size became about half. And when we use NDP compression only, it became to 50%. And if we use both compression techniques together, the table size becomes about 1/3. So using application level compression technique and a database level compression technique, we can gain a pretty good compression ratio. And next, we compress the stats table as well. In the original version, it had every row had 2 columns. One is at and one is CNT, which stood for hours since epoch and the number of hits. But it was a waste of space since most counter variables are mostly 1 or 2 or 3 or something like that. And that the most accesses will occur in a short period. And the third aspect was the art field should be part of the indexes to search fast. So it took extra space as well. So what we did is that we converted this into a sparse array and then compressed it. And for example, the example in the last page, one is converted to a sparse array like shown on the screen. And the size being compressed became 8 bytes of a tiny block. So it's roughly about 25% of compression ratio. And we store the array in a single column. So the number of columns became smaller, and it also made the system faster. And to use the compressed form, we created MySQL UDFs as well to access the compressed sparse array, like add counter to the sparse array of which index and the increment value, or to get the number of accesses from which hour to which hour, and more, those functions. And we also created a vectorized calculation UDFs to add a fixed size of array at once to create access charts. Because we have to do a 2-dimensional calculation, and using a vectorized calculation it makes the system faster, since we can do it row by row. And next, about the message queue. I created a message queue called QFOM, which runs as a pluggable storage engine of MySQL. And about QFOM, I talked it yesterday on MySQL conference, and the slides are available. So if you're interested, please see them. Next, about limiting pre-computation laws. We use cron and setlock to limit pre-computation. And in the example below, we call the everyday setlock without everyday operation without any options to setlock. And every 2 minutes we call setlock with -n. And -n means to use try-lock. So if pre-computation process is already running, their setlock will do nothing. But if there's no pre-computation logic running, then it will try to recalculate the hot entries. And for the daily task, there's no -n option, so it will always run. So by using this technique, you don't have to worry about cron processing piled up. So this is a good way to handle pre-computation. And to limit disk-intensive pre-computation, we use this logic. We calculate block by block and sleep by the time that took to execute the pre-computation. And we also created our own cache system as well. And the problem was that MySQL's query cache flashes every time a table updates. And Memcached has a thundering hard problem, which all clients try to read the database when the cache entry expires. And it was critical for us since our queries are heavy. So we created a cache system called Swifty and a mutex called kidmutex. And Swifty, what is the unique characteristic of Swifty is that it notifies a single client that tries to read the cache entry. It tells the client that the cache entry is going to expire within a few seconds. And the notified client can start updating the cache entry before it expires. So there will be no thundering hard problem. And the other module, kidmutex, works as a daemon. And it blocks multiple clients issuing same SQL queries. So by using these modules together, we can minimize our SQL queries. And the source codes are available here, so if you're interested, please see them. And next about the full text search. We use full text search engine called Sena and Triton, which Sena is a FTS engine which is very popular in Japan. And I'm afraid it might not work well with European languages. But anyway, it would work well with Chinese or Korean. And Triton is a replacement of MyISAM's full text search engine using Sena's backend. And it's much faster than MyISAM's FTS. And last year I wrote patches for Sena and Triton so that they can run well on SSDs. And the patches are now included in those libraries or software. And so actually, we downgrade the hardware from a RAM-based FTS server to a SSD-based one to see if it was actually possible. And the size of FTS data was around 20 gigabytes. And since we downgraded the CPU as well, the speed became about 1/4 of the original. But the latency of full text searches are still well below 1 second. So it will be just okay for most cases. So the summary is that UDFs are a very good point for optimizing your database access. And sometimes it is easier to scale up than scale up, especially when you can estimate your data growth. And using SSD for FTS is also a very good approach since it doesn't have a particular hotspot. And Baidu is also using SSD for their full text search. What's up? And most of the things introduced in this slide are open source. And we plan to open source our URL compression table as well. So if you're interested, please see my blog. And for the last thing, if you're interested in localizing Pastra to United States or your country, please contact us. So that's all from me. Thank you very much.